And today, we have the maintainers of the AFLplusplus open source project on stage. Dominic, Toka, Andrea, Edison, and Van Hauser will show us how this engine can be used with QEMU to fuzz binaries in a quite advanced way. Stage is yours. Thanks.
Thank you everybody for being here to our talk, Fuzz Everything Everywhere All at Once, Advanced QEMU-based Fuzzing. As we were just introduced by, we're the AFLplusplus project. It's a project we started in 2019 as a fork of AFL, which was one of the state-of-the-art fuzzers back then. Since then, we've added a ton of community features, and we started a new side project, which is LibAFL, which is a fuzzer that is very similar, but rewritten from scratch in Rust. And today we're going to talk about this LibAFL, we're going to talk about fuzzing in general, and we're going to talk about QEMU and how to use it for fuzzing in a pretty advanced way. If you want to know more about LibAFL and the underlying building blocks, you can check out our talk back from 2020 when it wasn't released yet, from RC3. And let's get to it. We've already been introduced with the AFLplusplus project. We're a large community of people where 5 of them are on stage, and there are more doing, on the side work, voluntary, vulnerable contributions. In this talk, first we're going to talk about fuzzing, the quick fundamentals of, about emulation with QEMU, binary instrumentation, and then we're going to have 2 nice examples. One is snapshot fuzzing of an Android library on a server that is not Android on 80 cores. And then we're going to show how to add sanitizers for injections, like SQL injections to binaries at runtime using QEMU. Right, let's fuzz. Fuzzing in a nutshell, at this time probably most people have heard it, at least stumbled upon it. It's just very simple concept. You rerun a program multiple times with a lot of inputs as fast as you can and try to find bugs and try to find crashes or other objectives like injections, for example, later. And then coverage-guided fuzzing is an evolved version of that where you basically track basic blocks or edges during your fuzzing. So some people may have, probably most people have seen a CFG, or at least if you code something, you by accident create a CFG, a control flow graph in your program. For every branch, you either go left or right, and sometimes you go back in a loop, for example. And each of these things is an edge in a control flow graph. And now the fuzzer can count how often one of these has been taken. And if it finds a new one, it'll use that as feedback and favor inputs that led to new paths. So it's like novelty search. You try to find new things and then mutate those further. And this makes fuzzing orders of magnitude faster over just no feedback, blind fuzzing. Now let's see what we can fuzz. We can pretty much fuzz everything if we can use quick emulator QEMU. It's a very popular full system emulator that supports a wide variety of instruction sets, such as basically everything you use every day. And it also has user mode emulation support where you don't emulate a full system, you just emulate one process. And all syscalls that would usually go to the host operating system go to QEMU, and QEMU translates it to the current host. And that we can abuse to change the syscall behavior later. How does QEMU work under the hood if you use it in emulated mode? You have the target binary. It executes one block at a time. You saw the CFG earlier. It lifts this block, if it's not cached yet, into an intermediate representation called TCG, Tiny Code Generator. And then it compiles it back down or assembles it back down or whatever you want to call it into the host architecture. So it would take an ARM binary block, one block of code until the next jump, lift it, and then drop it back down for the next architecture, for the one we want to run it on. Right, and now the cool thing is that in the meantime we had it in our hands, right? The emulator lifted it, and now we can add instrumentation there. What exactly is instrumentation? It's altering the behavior of the code. And that is pretty nifty. Usually you do that at compile time, but here we can do it at runtime. Sweet. Now LibAFL. Toka is going to talk about this part.
Thank Thank you. Thank you, Dominic. And I'm going to introduce about LibAFL, our framework, a bit. So we already have a state-of-the-art fuzzer, which is called AFLplusplus. And indeed, it does work. It can find bugs. But sometimes the problem is that you have a very special target that you want to write a custom fuzzer that is adapted to your very special target. But the problem is that when you have a custom fuzzer, when you write a custom fuzzer, first you're reinventing this wheel. You're going to write the same code again and again that the past fuzzer has written the same thing, but you're going to rewrite the same thing again. Also, those fuzzers typically has a very naive design. For example, usually you just have a mutator that is changed from the past fuzzer, but the other part of the fuzzer is just the same as like the scheduler or the other component is just very naive. Also, the scaling is a very hard problem, which we will introduce later. So basically, the fuzzers share the data via file system, which makes it hard to scale across multiple cores or multiple machines. So our solution is LibAFL. We adopt some of the state-of-the-art fuzzing techniques, including from the academia or industry. Our framework runs on is portable. It runs on some computer that does not have any standard library. Also, it is very extensible. The users can write any kind of modules to extend the existing module that we already have in LibAFL that is tailored to your custom needs. So it is scalable. It scales across multiple cores. Finally, it is very performant. Thanks to the compile time abstraction, we benefit from the Rust language. So here's the high-level design of LibAFL. First, we have the core library LibAFL core. The LibAFL targets the runtime code that lives in the target. Also, the compile wrapper, LibAFL CC, and many instrumentation engines like Frida or QEMU. So apparently, QEMU is the most important part in our talk. We have support for user and full system mode QEMU based on QEMU 8. The point of QEMU emulation is that sometimes the source code is not there, and compiling but even if you have the source code, compiling the code and dealing with the tool change is hard. So we can just use the binary to instrument the program and fuzz it. We can also change the instrumentation at runtime using QEMU. That is another benefit of it. And we also have another advantages of QEMU over other dynamic binary instrumentation engines. One of the advantage is the cross-architecture support. You can run any architecture like MIPS or PowerPC or ARM on top of it, and it's reasonably fast while being stable, which is why we adopt QEMU. So nextly, Andrea is going to explain the details of LibAFL QEMU.
Hi. So, we want to fuzz also everywhere. To fuzz everywhere, we want to fuzz some code that runs on another machine, another system, on our, for instance, desktop machine. To do so, we use LibAFL QEMU. And before showing an example of for the Android library that Dominic talked about before, we need to understand a bit the inner working of LibAFL QEMU. LibAFL QEMU is based on changing the behavior of the JIT compiler of QEMU itself, and it's based on some hooks. These hooks are the callbacks, basically, that are inserted by placing calls in the translated code of the JIT, so the code that it's the OTS code that is recompiled. by QEMU. And these calls call the callbacks in Rust that the user writes to do instrumentation, mainly for logging things that are useful for fuzzing. In this case, there are the hooks for the edge coverage hooks, in which a callback is inserted at every edge of the control flow graph. So we have these hooks that the user can use for edge coverage instrumentation, logging a unique ID, and for the coverage map. If you are into fuzzing, you know that we use coverage map, and for the more advanced people in the audience, this is the first case in which we have binary-only fuzzing with emulation, with unique IDs, and so collision-free coverage map. There are many kinds of hooks and instruction blocks and memory load store, comparison, but also like hooks before and after syscalls to build syscall filters. We will see later for scalability, for instance, to crashes and so on. So another important part of the design of our library, our LibAFL QEMU, is how the interaction between the fuzzer and the guest code is done. The execution control happens in 3 different ways. One is with a backdoor. A backdoor is like a hypercall when we talk about hypervisors. It's a custom instruction that is not defined for any of the QEMU architectures. Then the target itself. So when you write the harness, you want to insert this backdoor instruction. And the target itself asks the fuzzer to stop the execution of the emulator and go back to the fuzzer. Then there are the breakpoints, like classic breakpoints, like in any other DBI. So the fuzzer set a point in which the execution should stop, and then the execution stop, and the fuzzer get back the control. And then the very nice things that we have are the custom GDB commands. So you may know that in QEMU you can use GDB to debug the target code. And with the custom commands, the user can create commands to do something like, while debugging the gets code, like the user is debugging till one point, and then with the custom command you can say, for instance, okay, we reached in the debugger an interesting position, let's start fuzzing from here, from the debugger. So the next part is about, it's a quick and small example how to use LibAFL QEMU. We took a very widely known library that is not a normal one. Let's say it's running on another architecture than our desktop computers and in another operating system, in this case Android, a Samsung firmware on ARM64. And this library was targeted in the past for many different research. In this case, Project Zero targeted the image parser, this library QRAM that is an image parser, for the MMS exploit. Then Flanker did a talk on reverse engineering this library and fuzzing this library with a custom fuzzer. So like we have here this problem of writing custom fuzzers and at the real world CTF. So we followed the path of this research, and we reverse engineering again this library, taking the function that were fuzzed before by these researchers. We got into the interaction code between the Java part and the image library, so the bridge, you know, the NDK library part, that is the bridge between Java and the C library. And so we build in C, removing all the Java NDK usage in this library. We build an harness in C that is not this one. This is a very simple harness, just to show, but then we have a more complex harness using more API to decode the DNG format parser of the QRAM library. And then with this harness that we built to show up the capabilities of the library to fuzz on Android code, we built a fuzzer with LibAFL QEMU. So let's just discuss this fuzzer. This fuzzer is running inside the emulator, the target library, in which there are some hooks going on, mostly the syscall hooks, because we need to hook and block some syscall and replace the behavior of some syscall to make the library run on our system. And then also we grab the file system image of the firmware of Android, and we use it to run inside QEMU all the libraries on which the QRAM library depends on. So let's show a bit some code. Don't worry, you don't need to know Rust at this stage. I want just to show the API, how easy it is to load things inside LibAFL QEMU. So LibAFL QEMU is a library, no? It's not, QEMU is a tool, LibAFL QEMU is a library, so we build this API around QEMU. In this case, we start the emulator, we resolve the symbol of the harness, and then we set a breakpoint and run until the harness. Then we want also to set the breakpoint to the return address of this function, so we can loop over the harness, because the fuzzing is we can describe it in a very high level fuzzing as a loop, no? And then we save the CPU states to restore it later during the execution of the harness. And this is the harness. The harness is executed many times inside the fuzzer, so it's the thing that is run constantly at every fuzz case. And the harness is a callback. We get the input generated from the fuzzer. And with this input, we save it to a file, because the library is reading it from file. We run until the return address, and then we roll back the CPU state. In this case, we have some hooks, and there are the helpers that are collection of hooks that are already available in the library. So you can write your own hooks, but there are already built-in things in the library that you can use. In this case, for edge coverage and other things. And then this is the fuzzer running on one core. It's very simple fuzzer, like few lines of code plus the code for LibAFL to set up a fuzzer. And we have the fuzzer running with decent speed, because it's a very wide library. And it can find bugs, but we can do better. We can do better building a more complex fuzzer. How? We can do snapshot fuzzing, because not all the code in the library or in any other target is stateless, sorry. So there are code that leaves some traces in the state of the program that we cannot restore just by restoring the state of the register and the CPU. We want a sanitizer to uncover silent corruptions, I don't know, double freeze, for instance. And we want to scale, not just one core. So in LibAFL QEMU, there is a runtime built on top of the LibAFL QEMU hooks to do address sanitizer, that tracks the heap allocations, tracks the memory load and stores, and so on, to catch these silent if corruptions, much like, I don't know, Valgrind or Dynamo-Re or address sanitizer and so on. And then there is this, the ability of doing user space snapshot, and that are written from scratch, in which we use the memory load store and the syscall hook to track the dirty pages when the memories change, to track the changing of the memory mappings, like if, I don't know, the process starts to unmap random pages, and then we have to restore them if we want to continue fuzzing and restore the state of the program, and so on. And this is a little demo of the fuzzer running on 80 cores that is started. We can see the file system of Android that we downloaded from the vendor website. And we set for QEMU this file system to be loaded. So we are saying to QEMU, okay, we have to grab our dependent libraries from this file system. And then we start our fuzzer, giving the images as an initial seed corpora, the output, and the number of cores. And yeah, it's running. Then after a few hours, we get this, that the status screen of the QEMU address sanitizer in LibAFL QEMU of a bug that we found, probably an old one. And you get information, stack trace, state of the register, and so on, anything useful for crash analysis. So now, after this, Addison will introduce you how we scale over core, how this specific example on Android scale over cores, but also in general how LibAFL scale over core machines.
Thank you.
I told you.
So to get started, let's talk about actually why we need to scale in the first place. So fuzzing on one core is great. That only allows you to actually utilize one of your cores, right? We have many cores available to us on modern systems, so we would like to use all of them. The problem is that the scaling problem is quite hard. If we don't share events between different instances of the fuzzer, then we will waste a lot of time doing the same thing over and over, trying to find the same code regions over and over, observing the new things over and over. The problem is that communicating between the instances necessarily slows them down. As you can see here, this is a graph of the executions per second over versus the number of cores utilized. And actually, what's amazing here is that with old AFL, there gets to a point where you add too many instances and it actually slows the global executions per second down, meaning that you actually lose performance by adding new cores. And some of the reasons for this could be that we're just not using very good communication strategies. Suppose that we communicate over the disk when we're sharing the new inputs that we were trying to use. We're using a network to send events between them. We're using intermediate restarts to just reload the set of inputs that we have available to us. Something else, generally not very good. So what we implemented was something called the lower level message passing algorithm, which is essentially where we have a centralized broker which initializes each of the fuzzer instances. Now, what it does to do so is it launches the fuzzer instance and then opens a shared memory region with that instance so that it can communicate bidirectionally. So let's say that one fuzzing instance has an event occur, such as the discovery of a new test case that increases coverage in the program. What will happen is the fuzzer instance will send that to the broker, and then the broker will distribute that to each of the fuzzing instances all over shared memory, meaning that there's no kernel I/O or any other overhead-inducing operations occurring. And what this allows us to do is that we can scale up dramatically. Here you can see the sections in green represent the amount of execution that's spent in userland, in other words, not being used to actually interact with the system, and the red representing kernel interactions that will slow us down necessarily. We're losing time, not actually executing the target. And just to show you the results here, we have two different situations. AFL on the left, which is the historical data for AFL scaling that I showed earlier, versus LibAFL with LLMP. And you can see that LibAFL with LLMP scales nearly linearly over cores. And in effect, what this allows us to do is we can use the same fuzzer that we used previously, but instead of getting 5,000 to 8,000 executions per second, maybe we can get upwards of 500,000, which is great. So next, I'm going to invite Mark to come speak to you about how to catch injection-style vulnerabilities using QEMU as well.
Please. Thank you. Why is fuzzing so popular? Fuzzing is great because it finds memory corruption vulnerabilities. And 80% of the critical vulnerabilities are memory corruption. So that's why fuzzing is so hip. Everyone wants to do that. And there is a large focus on that. But the problem so far is we only find memory corruption vulnerabilities with traditional fuzzing, like we do currently with AFL, HongFuzz, LibFuzzer, etc., etc. So what if we could find other type of bugs that we are interested in exploiting? That was so far very difficult. We need very different tools, like for example SQL-map, to be able to find SQL injections. But they work on a web server that we have to talk over the network. We don't have coverage there. So this is very, very limited what we have with other kinds of fuzzers that we can use to find other kind of vulnerabilities. Though the idea is finding injection vulnerabilities while doing normal AFLplusplus, LibAFL style fuzzing. So how do we do that? Basically, we are using LibAFL QEMU user mode, and we use hooks. And the idea is basically so super simple that I was surprised nobody ever thought about doing that before. So basically, we just hook SQL functions, LDAP function, HTML output functions, and then we just check the parameters if there's anything suspicious in there, which means stuff that would create an injection vulnerability that was not sanitized. And if we detect this, well, we just crash and the fuzzer picks that up and we find an injection vulnerability. So it's that easy. And the added advantage that I did in the implementation here for LibAFL is we can customize it with an easy script. So a picture to make it a little bit more easier to understand. We have the standard LibAFL, LibAFL QEMU, where we run the target scaled to 100 cores if we want to, with snapshot fuzzing and everything. And we just fuzz normally, but we added hooks to specific functions, for example, for SQLite, for LDAP, to hook the system call, etc., etc. And whenever they are called, we check the parameters. If there's anything that would trigger an injection vulnerability type, we crash it. And we find this kind of bug. To make this super easy to configure, so you can use it on anything, and you could use it on CSV injection vulnerabilities, XML injection vulnerabilities, any kind of injection vulnerability you want. Or even you could do something like data loss detection, secret loss detection, for example, while fuzzing. You just configure it in a configuration file, where you say, hook these kinds of function. It's the first, second, or third parameter that you're interested in. This is the input test that you add to the dictionary, and then you have a match value, which is basically if this ever comes up like this in the query parameter, crash the target, and we have found an injection vulnerability. That there are false positives, this is something we don't like in fuzzing. False positives are unlikely to happen if you set up your configuration correctly. So with the injection string and the match string. If you set this up correctly, there is basically no chance of a false positive. Of course, false negatives will happen all the time. This is that are bugs that you're not finding, that you're not triggering. But this can be, the better you set up your injection handling, the more of these vulnerabilities you will be able to find. And as I said, there is no limit to the type of injection vulnerabilities you can. It's basically up to you to set it up and make it work. And we have lots of examples for command injection, for LDAP injection, for SQL injection, now, but you can already just deploy and use. And we can find these kinds of bugs by doing the normal kind of AFL, LibAFL fuzzing for memory corruptions with QASN, etc., etc. Here's a small example. So a little test me file which has an SQL injection and a command injection vulnerability, no memory corruption vulnerability. I run it with our QEMU fuzzer with the injections YAML file where I have defined several target functions to trigger, and it immediately finds the SQL injection vulnerabilities and the command injection vulnerabilities. It's really that easy. So. Yeah, that's already it. For me, I'm the main AFLplusplus developer, not LibAFL developer. But even for me, with very little knowledge of Rust, actually, because I'm more a C coder, it was super easy to implement. And that's basically the strengths that we have with LibAFL. Now, LibAFL is open source, so join the cult. We have so many contributors, so many other projects depending on LibAFL to write their own customized fuzzer. Yeah, what we showed you is that basically with QEMU we can scale, we can fuzz, we can detect even bugs that are not immediately resulting in a crash because of QASN, for example. Yeah, we can rehost, we can fuzz Android stuff on our systems or on a Mac. We can hunt for injection vulnerabilities, and we have massive speed with that. And that's just 5% of the features that LibAFL has. So just 30 minutes of presentations, but we could basically do 5 to 6 hours and still show you more features and how to use our LibAFL API to build successful and good fuzzers. Yeah, and I want to use this opportunity to thank our team. We're 7 people from 5 countries. And it's such a pleasure to work with so talented, skilled people, and we're able to, well, before Google was developing the 3 most best fuzzers in the world. But yeah, we made it possible that the best 2 fuzzers in the world are now written by us. Yeah, fuck Google. Oh, and we have perfect timing. Time for questions.
Indeed. Thanks, everybody. So, do we have any questions? What about the internet? Yes, there is an internet question, please.
Yeah, the internet would like to know, can hardware crypto be emulated as a peripheral in QEMU, and can LibAFL be applied to the hardware crypto calls?
You want to take that?
Hardware protocols, I don't think you can use... Yeah, you're right. But the couch was more comfortable. So hardware protocols, you mean like in the drivers of some firmware operating system that is interacting with hardware, no? So you want to fuzz software that interacts with hardware. That is, you can do even you can fuzz even hardware, like not with QEMU maybe, but there are projects based on LibAFL that use that bridge the fuzzers, the LibAFL API to hardware simulators, and you can even fuzz the hardware. But if you want to use LibAFL QEMU to fuzz software that interacts with hardware, you need to implement your own devices, the emulated devices on top of QEMU. And this is still, or maybe you can do rehosting. But like most of the time, you have to write code into QEMU to like allow QEMU to run your firmware that used in your devices.
Thanks. Then microphone number 1, please.
Yeah, hi. How about symbolic execution?
Can you repeat?
Okay. What about symbolic execution? Have you thought about doing that? I mean, there's this S2E, of course, from Eurocom, from EPFL.
They want me to answer all the questions. Okay. Yeah, LibAFL, there are modules for concurrent tracing, and it's not... LibAFL QEMU cannot do symbolic execution at the moment. I don't think we plan to do it with the hooks in LibAFL QEMU. It can be, there are some modules to use SimQEMU, that is a concurrent executor based on QEMU, but then you don't have all the APIs to do the harness. And so it's not extensible like LibAFL QEMU. But in theory, you can bridge LibAFL QEMU fuzzer with SimQEMU to do concurrent tracing, so concurrent fuzzing.
Thanks.
Okay, and let's switch to microphone number 2, please.
Yeah, thanks for the great talk. You said that one of the advantages is that you can actually use, or you can actually change the instrumentation at runtime. Why would you use that? Or any examples of that? Maybe for optimization, but...
Like, imagine that, you know about, like, there are some techniques in fuzzing, like you need to do some more EV instrumentation. I don't know, for instance, with CMP-log, we track the comparisons, but also every function call with 2 pointer arguments. But we need to do it just one time for each test case in the corpus. So as this, like instrumenting every call is more heavyweight than instrumenting for edge coverage, every comparison and every call, we can actually like flash the JIT cache and retranslate the code with the heavyweight instrumentation, do our run with the heavyweight instrumentation that is taking, I don't know, 10 times more the normal run for just edge coverage, then reflash again the JIT and instrument with just edge coverage hooks.
So basically for optimization purposes?
Yeah, optimization or, I don't know, sometimes imagine you want... We don't do that. I can envision we could do, I don't know, concurrent fuzzing and normal fuzzing in the same process, just like flashing the cache with the symbolic hooks that are more heavyweight. You instrument every instruction, and then you flash it and you instrument for fuzzing or something like that. Yeah,
thank you.
Okay, the internet is curious. Please.
Yeah, why use a full-blown QEMU and not a lightweight fork built for it like Unicorn?
Because in Unicorn emulates only the CPU. I mean, we want to emulate processes, so system calls, that, and then Unicorn also it's kind of slow. Like the benefit of a user mode QEMU is that you use the MMU of the host operating system, so you don't have to emulate the MMU. The LTLB is much, much faster to execute the same piece of code, even if it's not doing any syscall interaction under QEMU user mode than Unicorn. And then also we share the code base with a full system QEMU, LibAFL full system QEMU, that was not part of the talk, but like is work in progress, almost finished actually. We can even snapshot fuzz windows at the moment, but like the API is changing very fast. So maybe stay tuned for the next Congress for another talk. Maybe. And so the entire point is also that we share a lot of code in common within user space as system mode.
Yeah, one thing to add to that, like there is, of course, fuzzing based on Unicorn, but the problem, the moment you hit any system call, you basically have to re-implement that, and there are like wrappers like shielding, for example, that basically build a full system in Python then, and that obviously is really, really slow in comparison to just using the host operating system to do these things.
But actually, you can use LibAFL with Unicorn.
Okay, thanks. Now, microphone number 3, please.
Yes, thank you for the presentation. In the past, I have also worked in automated testing, and one of the things that was quite common there is that we would run our software on, for example, the core utils to find bugs, and because most of the testing I know is just for memory errors, I just wanted to, did you find any interesting bugs with your injection detection?
I just developed this in December, so it's still work in process. So I contacted Google with the OSS Fuzz environment they have to let it run in their environment and just see how effective it is. So to see how many real-world bugs it can easily find or not. So this will be something I will hopefully know in February.
Yeah, but the...
So another part is that there has been some related work using command injection, and that has found several bugs in the OSS Fuzz framework.
One so far only, but yeah, at least one.
Sorry, not several. But.
It's the system sanitizer, yeah.
Okay, let's go back to microphone number 1, please.
Okay, thank you for the great talk. I have a question about the last part, about finding non-memory corruption vulnerabilities. The question is, often systems having such bugs, for example, command injections, are not written in binary languages, not in C or C++. So, and to fuzz programs in other languages, we have to get the coverage information, right? So, do you know some ways we could give the fuzzer the coverage information if we are fuzzing program written in Python or maybe in Ruby or in Java?
But that's the thing. You can already do that with QEMU. QEMU doesn't care if the program is running and was written in Rust or anything else. You just run it. And for command injection, this is syscall. This is kernel. You hook the kernel call. So it doesn't matter if you run QEMU on Python, which doesn't make much sense, but it would still work, and you would find the command injection even there.
But if we are fuzzing a Ruby program, it's not compiled, so we will see the coverage only for the
No, I got the question.
Part.
Like, you have to instrument the Ruby interpreter.
Yeah.
So that's already been done, like not Ruby specifically, but we've done this with LibAFL for both Python and for JavaScript in the past. So it's very much doable, and you can use something like the instrumentation passes from something like Jazzer to get the feedback for something like Java.
So there are open source implementations of that instrumentation, right?
Yeah, precisely.
Thank you.
Okay, thanks. Microphone number 2, please.
Okay, thanks for the presentation. I'm interested in the full system the thingy. I know that there's KAFL, which is running on Nix, and I understand that the ABI is very unstable. I'm just asking whether you can share the details just quickly. Are you using a patched KVM, or are you planning to upstream the patches? Because I know the snapshotting thing, performance-wise, is not the best.
There's snapshotting of a QEMU full system. We don't use it because they use a user fault FD that is very expensive. So, like, another guy in the team is writing a full system, like dirty page tracking, that is more efficient. And it's kind of working now, but few edge cases. We are able to like fuzz windows. And we do it in emulation mode because there is already Nix for KVM. We may plan to rewrite also the same thing of Nix with the same API in LibAFL QEMU maybe in the future. But what we want to do now is emulation-based fuzzing with QEMU. Because like for KVM, there is already Nix. And the fact that for full system QEMU, you are stuck to using very old tools or tools like Panda that is amazing but is based on QEMU 2. So like we really need something for emulation, for firmware fuzzing, for instance. So like you want emulation, you don't want to use KVM. You want emulation because firmwares are, I don't know, MIPS, PowerPC, and you want to fuzz them on x86. And like the full system that is work in progress, that is almost ready, is about TCG and emulation.
So you're trading off a bit of performance for more flexibility in that way.
Exactly.
Okay, thank you.
But also Nix is there is the LibAFL Nix bridge, and you can use LibAFL with Nix already. So like you.
Yeah, no, but the setup is very painful.
Okay, we're running out of time for this session here. I would say hands-on this type of approach.